Hello viewers, welcome to my channel ITJ Olympiads and AP Physics with Ambarish. So in today's video I have brought solution to Pathfinder Challenge Your Understanding Problem 5 from Thermal Physics. It's a very nice problem. It involves leakage of gas from one chamber to another. There's a valve and I found this problem to be really quite challenging. So that's why I've chosen this problem for today's video. I'll read out the problem statement and see if you want to try it out. You can try out it and then you can have a look at my solution. So let me formally read the question. Okay, so here it goes. A horizontal cylinder with a fixed partition and a piston at its right side wall is filled with helium gas. Okay, so there's a piston on the right hand side and there is a valve in between, and there is helium gas here also and helium gas here also. Okay, in the partition is a valve that opens when the pressure in the right part exceeds the pressure in the left part. So there is some pressure here, let's say P1, this is some pressure P2. So when this pressure exceeds this pressure, this valve will open. Okay, pressure in the right part exceeds the pressure in the left part. Area of the piston A is 100 centimeter square. This area is given as 100 centimeter square. Initially the piston is Li is equal to 112 centimeter away from the partition. So this piston is at a distance of Li is equal to 112 centimeter from the partition. Okay, area is given. Okay, and lengths of both the parts are equal. So initial length, this length is also Li, and let's say this length is also Li. Both lengths are equal initially. Okay, amount of the gas in left and right parts are 12 gram and 2 gram respectively. M1 is 12 gram, so this is M1 which is 12 gram, and this is M2 which is just 2 grams. Okay, so obviously I'll not give you any hint, so you can think about it. Okay, so M1 is 12 gram and M2 is 2 gram. Temperature in both the parts is Ti is equal to 0 degrees Celsius. So initial temperature in both of them is Ti. If you want, you can solve it in symbols, because that's what I've done in my solution. It's okay if you do not want to substitute the values, just see what symbols are given and express your answer in those terms. Okay, M1 is 12 gram, M2 is 2 gram respectively. Temperature in both the parts is Ti is 0 degrees Celsius. Specific heats of helium at constant volume and constant pressure are CV is 3.15 kilojoule per kg Kelvin. Please remember, this is not given in terms of moles, this is given in terms of mass. Okay, so mass specific heat is given. Okay, so CV is this much and Cp is 5.25 kilojoule per kg Kelvin. Okay, atmospheric pressure is P0 is equal to 10 to the power 5 Pascal. Walls of the cylinder, the partition and the piston all are made of good heat insulating materials. The piston is pushed into the cylinder, stopped for a while when the valve opens, allowing thermal equilibrium to establish between both the parts. So you are pushing the piston and that will increase the pressure in this chamber, and finally when the pressure, these two pressure become equal, the valve will open. Okay, and after the valve opens, you let the gases mix. I mean, it's the same gas but at different temperatures, and they are mixing, and you are allowing thermal equilibrium to happen. Okay, in both parts, and then further pushed until it reaches the partition. So after the valve opens, you wait for a while. After thermal equilibrium is established, again you push the piston all the way up to the valve. Okay, or you can say partition. There's a valve in the partition. Okay, find the work done by the force pushing the piston. Okay, so that's the statement of this problem, and if you want, you can pause the screen and you can try this problem for a while. It will take good maybe at least 10 minutes or so, proper analysis, or even more it can take. So I'll get into the analysis right away. Let's see. So this is the figure. I have copied the data. Area was given and initial length, this is 112 centimeter. M2 is 2 grams, this is 12 grams, and pressure is same on both sides initially. Okay, oh no, sorry, pressure is not same. See, mass over here is lesser than mass over here, and temperature here is same as temperature over here. So that means what? The pressures will be directly proportional to the masses. So this is 2 grams, volumes are same, temperature are same, so pressures are directly proportional to number of moles, and since it's helium on both sides, so P1 and P2 must be in the ratio of 2 is to, or rather 12 is to 2. Okay, CV and Cp are given. So what I've written, since all the boundaries are perfectly insulating, all the processes are happening adiabatically. Of course, no heat can enter from anywhere to anywhere. Okay, So it's only the work that's being done on the system, and therefore every process is adiabatic. Could be reversible or irreversible, but it is definitely adiabatic because there's no heat transfer happening anywhere. Since the volumes and temperature of the chambers, volumes and unnecessarily put off. Since the volumes of the chambers and the temperature of the chambers are equal, the pressures must be proportional to the enclosed masses in the chamber. So that's what I said a little while ago. And then since there is no heat being supplied, the net change in internal energy of the gas must be equal to the sum of the work done by atmosphere and the pushing force. See, when we are pushing the piston, atmosphere is also doing some work and our force is also doing some work. So total internal energy change must be the sum of the work done by atmosphere plus work done by us. Okay. So if that's settled, I can proceed with the calculation. So now what my strategy will be, I'll find the delta U in the first stage. First stage is until the valve opens, and after that I'll try to calculate the temperature, and I'll then try to find out the internal energy in the second stage, that is pushing the piston from the valve opening configuration to the configuration where piston is touching the partition. Okay, so let's look at the first stage. Okay, now for adiabatic process, all of you must be knowing that pressure into T to the power gamma upon 1 minus gamma is constant, or sometimes it's written as P to the power 1 minus gamma into T to the power gamma is constant, or it's the same thing. Okay, so this pressure is P1, and let's say this pressure was P2 here initially, and the piston is pushed until the valve is opening. So I can say that P2 into T initial to the power gamma upon 1 minus gamma should be equal to, now let's say here at the time of opening the valve, this temperature has become T2. So this is equal to P1 T2 to the power gamma upon 1 minus gamma. And if you rearrange this equation, you get T2 is equal to this P2 by P1 to the power 1 minus gamma upon gamma Ti. And you know that P2 by P1 is same as M2 by M1. Why? Because initially both the chambers had same volume and same temperature. So pressure must have been proportional to the mass ratio itself. Okay. So I hope this is settled, why I have replaced P2 by P1 by M2 by M1. Now delta U in this step will be what? Delta U will be M2 CV delta T, M CV delta T. Okay, just like there you have N CV delta T when molar specific heat is given. So now until the valve has opened, whatever internal change is happening, that's happening only for the right chamber. So, and that mass is M2, so M2 into CV into delta T, that is the delta U for the right chamber. Okay. Now now I can substitute for delta T. So final temperature in the right chamber is this one, and the initial temperature was Ti. So just subtract and then substitute. So this is our delta U in the first stage. So change in internal energy until the valve opens. Now what will happen after opening of the valve? Hot gas and cold gas mix, and still total internal energy is conserved. Why? Because there is no delta Q and there is no delta W happening during the mixing part. Okay, so and internal energy is proportional to the product of mass and temperature. So you know that internal energy for molecule is half mv square, and v square is proportional to temperature. So we can say internal energy is, total internal energy is proportional to the mass and the product of mass and the temperature. Now let T3 be the equilibrium temperature upon this mixing. So I can say that M1 into Ti, see left chamber mass is M1 and the temperature is Ti, and here mass is M2 and temperature is T2. So I can say that M1 into Ti plus M2 into T2 must be equal to M1 plus M2 into T3. T3 is the temperature after mixing. And if you rearrange this equation and you substitute for T2, I have already found T2. See, I found T2 here. This is T2. Okay, from equation 2, if you substitute T2 and you rearrange this equation, you get T3 is equal to this much. Okay, so this is the temperature after the thermal equilibrium is established upon opening of the valve. Now we wish to find internal energy change in the second stage, that is further pushing of the piston. Okay, I have not completed the sentence, so word, so it is upon further pushing of the piston, or maybe somehow it got erased. Okay, so now see, once the valve has opened, some of the students may have a doubt that will the pressure change, or can the valve close again if the pressure changes. So the thing is, you can easily see that the after the valve opens, it's not going to close again. Why? Because even after mixing, the pressure has to be same. Why is that? Because internal energy is F by 2 RT, NF by 2 RT, or you can say F by 2 PV, and F, where F is the degrees of freedom. Okay, so F by 2 into left side pressure is P1 into this volume, and then again F by 2 into this pressure into this volume, and these two pressures are equal, should be equal to F by 2 into final pressure into V1 plus V2. And since P1 and P2 are these two pressures are already equal, so that means what, final pressure is also going to be same, so there's no chance of valve closing again. Although it's not explicitly mentioned in the problem that valve can close again, but there can be a nice problem where a valve has the possibility of closing again, but still it will not close, because even after mixing, because of conservation of internal energy, and since internal energy is F by 2 PV, the pressures are not going to decrease even after mixing. Okay, now we need to find the final temperature after the final push. So I'm pushing this piston and until it reaches the partition. Okay, now let this temperature be T4. So now once again this process is adiabatic, so I can say TV to the power gamma minus 1 is constant. So I can say now final temperature after this is pushed, let's say this temperature is T4, and entire gas is now confined over here only, and this piston is touching this. So I can say that T3 now, and also you realize that since area of the cross section is same, so volume is nothing but it's proportional to this length. So let's say this length is Li, and let us say this length is L2. So this volume is proportional to L2, and this volume is proportional to Li. Okay, and entire volume is proportional to Li plus L2. So I can say that T3 into Li plus L2 to the power gamma minus 1, I am applying this equation, is equal to T4 into Li to the power gamma minus 1. And what does that give me? That gives me T4 is equal to T3 into 1 plus L2 by Li to the power gamma minus 1. So now if I somehow can calculate L2 by Li, then I am done. I'll have T4, and once I have T4, I have T3. I can easily calculate the chain internal energy as mc delta T. Okay, so now what to do with this L2 by Li? So this is the last thing that I need to calculate, and after that you can see the road clearly. Okay, so what do I do for L2 by Li? Now initial push was also adiabatic, so I can say that P2 into Li to the power gamma should be equal to P1 into L2 to the power gamma. What do I mean by this? See, right hand chamber, let me go back to the initial figure. Right hand chamber initial pressure is P2, okay, and initial length is Li, and this piston was pushed, so I can say that P2 into Li to the power gamma should be equal to, now finally when this valve is about to open, this pressure is P1, so this is equal to P1 into L2 to the power gamma. So I hope you understood that, because the initial push was also adiabatic. Okay, so since initial push is also adiabatic, I can say that P2 Li to the power gamma is equal to P1 L2 to the power gamma. That means what? I can say that L2 upon, this should have been Li, L2 upon Li should be equal to P2 upon P1 to the power 1 by gamma, just rearranging this equation, and therefore L2 by Li and P2 by P1, I told you that pressures will be proportional to the initial pressures will be proportional to the initial masses. Why? Because volumes were equal and the temperatures were equal, so pressures will be directly proportional to the number of moles or mass content in the chambers. So P2 by P1 can be replaced directly by M2 by M1, and you can put this M2 by M1 over here, and now you have the temperature T4. And now once you so if you simplify this is just a part of simplification, this is what you get for T4, and delta U for this step will be what? That will be equal to M1 plus M2 into CV into T4 minus T3. See, delta U is MC delta T. Like for molar heat capacity you can write NC delta T, so it doesn't matter what the process, so delta U is always NCV delta T, even if it's an adiabatic process or whatever, it doesn't matter. So don't think that it has to be isochoric process for delta U to be M1 plus M2 CV delta T. This is a standard thing that you learn while studying thermodynamics theory. So now substitute for T4 and T3 and you get delta U2 in the second stage as this value, and now work done by the pushing force on the piston, this force, and plus work done by the atmosphere. So how much work will be done by atmosphere? See, this piston area is A and atmospheric pressure is P naught. So P naught into A is the pushing force, and atmosphere pushes it through a distance of Li. So atmospheric work is P naught into A into Li, and that should be equal to delta U in the first stage plus delta U in the second stage. So I can simply write work done by this pushing force is delta U1 plus delta U2 minus P naught A Li. And now I can just substitute for delta U1 and delta U2. So here is the delta U2 and delta U1 I had found earlier. Let me show you. Delta U1 is this, equation 3. So from equation 3 we have delta U1, and then this equation we have delta U2. So just substitute and then you get the expression for total work done by the pushing force. So that was my analysis of this problem. A lot of steps in this, a little bit complicated, but I'm sure you would have understood it. If you heard this carefully, you must have understood the solution to this problem. And if you did like my solution, please do give a thumbs up to my video and share this video as much as possible in various WhatsApp groups or Telegram groups or Discord servers or whatever media you use for networking with fellow students for your academic discussions. And most importantly, if you have not already subscribed to my channel, please do subscribe to my channel, for that is what keeps me motivated to post newer and newer videos. Please do keep coming back to my channel, for more awesome stuff would be coming on this channel. Thanks a lot for watching this video, and I'll see you in the next one, and God bless you all.